Hi, Spark and Summit and AI attendees. I'm glad you could join me for my virtual talk. Today, I'll be talking about some of the lessons we learned from building Databricks' large-scale multi-cloud data platform. First, an introduction. I'm Jeff Pang, and I'm a principal engineer at Databricks in our platform engineering team. Databricks helps data teams solve some of the world's toughest problems, and the Databricks platform team's mission is to provide a world-class multi-cloud platform to enable us to expand fast and iterate quickly so that we can continually improve our product for data teams. If you're interested, you can find more information about our platform team at databricks.com/careers. As you may know, Databricks was founded a few years ago by the original creators of Apache Spark. We provide a data and AI platform that now serves more than 5,000 customers in a variety of industries. We're still a startup, but we've grown to over 1,000 employees, over 200 engineers, and now have over 200 million in annual revenue, and we're still growing. Our data platform provides unified analytics and AI to data scientists, data engineers, and business users. It includes a data science workspace that integrates tools like notebooks, MLflow, and TensorFlow. It also has a unified data service built on the best-in-class deployments of Apache Spark and Data Lake. And it's built on top of an enterprise cloud service that's simple, scalable, and secure because we manage all of the operations for our customers. So what's in this talk? First, I'm going to take you inside our unified analytics platform and show you a bit about how we architected our multi-cloud data platform. Then I'll describe 3 challenges and lessons that we learned while building it. First, how we grew and evolved our data platform over time. Secondly, how to operate successfully in multiple clouds. And finally, how we use data and AI to accelerate the data platform itself. But first, let's look at the architecture of the Databricks data platform. So in a simple data engineering architecture, you might use a single Spark cluster to process your data from your data lake, which could be data stored in S3 or HDFS, for example. You might take this through bronze, silver, and gold stages of data processing pipeline to refine the data for use. And finally, you'd have analytics and reporting applications on top of this data to actually provide value for your users. Now, most modern data platforms actually involve many different data pipelines, not just a single one. They would involve streaming data in addition to your data lake and might involve scheduling more complicated workflows where the output of one job is processed by the input of another. You probably use a modern data format like Delta, and your applications would involve streaming analytics, notebooks, machine learning, AI, and probably more. And to do all these things, you'd probably need many different Spark clusters for scale. And to manage these Spark clusters, you'd probably need some cluster management system like Mesos or Kubernetes. This is the type of architecture that many organizations are using or trying to build in order to get more and more value out of their data. The Databricks data platform provides this for thousands of our customers. We manage a control plane which handles the analytics, the collaboration, AI, workflows, cluster management, reporting, business insights, security, and more, so that our customers don't have to manage that themselves. And we manage many Spark clusters in our customers' preferred networks to process the data from all of their existing streaming and data lakes. Furthermore, our data platform is deployed in many regions throughout the world because we have customers deployed everywhere, and it's critical for the data platform to be close to the data. And because our customers have their data in more than one cloud, we replicate these deployments in several clouds and integrate with the best features of each of these clouds, such as AWS and Microsoft Azure. The Databricks data platform thus is a global scale multi-cloud platform that manages the data platform for thousands of customers around the world. As a consequence, the Databricks data platform manages millions of virtual machines on Spark clusters every day. As you can see from this graph of VMs managed per day, we anticipate that the scale of our data platform will continue to grow pretty rapidly. That's the Databricks control plane, the control plane of our data platform in a nutshell. And that's what will be the subject of this talk. Our control plane has hundreds of thousands of users, hundreds of thousands of Spark clusters every day, millions of VMs per day, and processes exabytes of data each day. Our data platform supports everyone from university students just trying out Spark for the first time in our free community edition to Fortune 500 companies with thousands of users and many complex workloads. In the remainder of this talk, I'll discuss some of the big lessons that we learned from building this large-scale multi-cloud data platform. The first challenge I'll discuss is how we grew our software as a service data platform over time. As a startup, we obviously didn't start out with a global scale multi-cloud data platform. In fact, we started off with something pretty small. The challenge was how to grow a data platform that provided a lot of value for one customer to thousands, all within a span of a few years. Since we managed the data platform for our customers and we wanted to keep expanding the capabilities of what our customers could do with it, we learned that the data platform itself isn't actually the most important thing. Actually, it's the factory that builds and evolves the data platform is more important than the data platform itself, because that allows us to rapidly provide more value and support more use cases in our data platform over time. And this happens all in a way that's transparent for our users. So what were some of the keys to success in building a great data platform factory? First, we needed to quickly deliver value to the market. For example, we provided a version 1 of our data platform, which included some analytics tools like notebooks, but very quickly had to provide a version 2, which included more features like job scheduling and management. The challenge in quickly iterating on our data platform is that our users are using and relying on it at the same time that we're trying to change it. So we need to be able to make sure we don't break things while we're continuously changing this data platform. The keys to success in establishing this virtuous cycle are our modern continuous integration infrastructure, fast developer tools, and a lot of testing. For example, at Databricks, we make heavy use of Scala, Bazel, and React.js for our developer platform. We spend a lot of time optimizing our Scala builds to get up to 500x speedups compared to default tooling, for example. And we run tens of millions of tests every day to make sure that our changes don't break things. Our developers also create hundreds of Databricks in a box, full control plane environments every day so that it can develop, test, and demo new features. This allows us to keep adding new features to a data platform very rapidly. Secondly, we need to very quickly expand the total addressable market by replicating our control planes in many environments. The challenge is that each environment is slightly different. There are different clouds, different regions, and different data governance zones that require different configurations. So this quickly becomes very complex if we want to support all these different environments and iterate quickly to update them with the latest features. The keys to success to expand quickly for us was to focus heavily on declarative infrastructure, where we rely solely on templates that describe our different control planes and use a modern continuous deployment infrastructure to deploy them. At Databricks, we use a templating language called JSONet and Terraform and Spinnaker to form our deployment pipelines. This allows us to express over 10 million lines of configuration, for example, and many fewer lines of code. And it allows us to deliver new features in our data platform globally several times each month. Finally, we wanted to expand the workloads that our customers could run on Databricks after they've adopted our data platform. This meant that we needed to expand the scale at which our data platform could operate, and simultaneously scale the rate at which new features could be added to the data platform over time. As more and more of our engineers develop features for our data platform, we needed to make sure that they weren't reinventing the wheel and building everything that everyone else has already built. The first key to success in scaling quickly within customers who had already adopted our data platform was to have a service framework that did much of the heavy lifting for all data platform features. Things like container management and replica management, APIs, RPCs, rate limits, metrics, logging, secret management, etc. These are things that all features and all teams at Databricks need in order to build their features. From notebooks to SQL to MLflow. These are all pieces of our data platform, but they aren't really core to their functionality. The second key to success was to decompose our monolithic services into microservices. For example, when we first started, our cluster manager service, which manages all our Spark clusters, was a single machine. And it just managed a few hundred VMs for a customer. But to support the millions of VMs that we manage today, we needed to break it apart into different core functions so that it could scale. A well-rounded service framework was the key to doing this rapidly so that we could spin up new services with different functionalities very quickly. So in summary, the Databricks data platform factory allowed us to iterate on our data platform very quickly, rapidly replicate it in many regions and many clouds, and expand the scale and breadth of workloads that it could support. One of the great things about having a solid platform factory is that we often use it to improve the factory itself as well. You can see from this diagram that we use a lot of cloud-native open source technologies at Databricks. Everything from Envoy and GraphQL for RPCs and APIs, to Kubernetes for container management, and Terraform and Spinnaker for deployments. But we didn't actually start out with all these technologies. Heck, when Databricks first started, many of these open source projects didn't even exist yet. But by taking a factory approach to our development process, we continuously retool our factory and incorporate and extend the best tools out there over time, essentially using our factory to improve and refine itself in addition to our data platform. Next, let's talk about how we run Databricks on multiple clouds. Databricks runs on multiple clouds, including AWS and Azure. Why do we do this? Well, because the data platform needs to be where the data is. Putting the data platform in the same data center as the data impacts performance, latency, and data transfer costs. It allows us to integrate with the best features of each cloud and allows us to adhere to the data governance policies that our customers demand from our desired cloud. The biggest challenge in supporting multiple clouds is to do so without sacrificing the velocity of feature development for the data platform itself. As I just mentioned, iterating quickly was the key to extending and expanding the data platform, and we didn't want to sacrifice that. What we found is that a cloud agnostic platform layer is the key to maintain developer velocity. But this layer also needs to integrate with the standards of each cloud and manage their quirks. So in the next slides, I'll discuss what I mean. The developer experience on multiple clouds is pretty divergent, so it's pretty hard to build the same thing on each cloud. For example, many cloud services have no direct equivalents. For example, in AWS, AWS has a great scalable key value document store called DynamoDB, but the same interface really doesn't exist in Azure. Cloud APIs also don't look anything like each other. Even the authentication and access control in each cloud is very different. Operational tools for each cloud is also very different, and you can't even consume logs in the same format. This makes it pretty challenging to support multiple clouds without doing a lot of extra work. To overcome this, we built a cloud-agnostic developer platform to support our data platform. Between these blue lines here are services that make up our data platform, things like SQL, notebooks, job scheduling, MLflow, cluster management, etc. To make sure that these services can operate seamlessly in multiple clouds, we developed a service framework API that's common across the different clouds that we support. This API builds on a few lowest common denominator cloud services that are pretty similar on each cloud. Things like virtual machines, networks, databases, and load balancers. When a Databricks engineer works on a data platform service like MLflow, for example, They would use our service framework API to manage APIs, RPCs, users, permissions, billing, testing, and deployment, for example. They would write the code once, and they wouldn't need to worry about the differences in each cloud. It would just work. Now, we learned that not everything can be cloud agnostic, no matter how much we try to abstract away the details. First of all, customers actually want to integrate with some of what is best about each cloud, and we want to support the standards of each cloud. Second, even lowest common denominator cloud services like VMs have implementation quirks that reveal themselves once you start building on them, and therefore they're not exactly identical. To handle integration with the standards of each cloud, our service framework also acts as an abstraction layer for the differences in each cloud that we have to integrate with. For example, the ways that each cloud do authentication and authorization, key management, billing, and storage are pretty different. Yet most data platform features need to deeply integrate with all of these properties. So to harmonize the differences in each cloud, our service framework API abstracts away the differences as much as possible so that a service and data platform feature like MLflow just needs to know about our service framework notion of authentication and key management rather than that of each cloud. So for example, it wouldn't need to know about like KMS or Azure Key Vault. It would just know about our own notion of bring your own key for encryption. For example, consider storage. Storage is a very special example because both S3 and Azure Data Lake are the most common and cost-effective ways to store large data objects in each cloud. And typically, these storage layers typically form the basis for data lakes that most of our customers use. However, S3 is eventually consistent, whereas Azure Data Lake is strongly consistent. So they have pretty different semantics. That is, after writing a file into S3, the next read of the same file isn't guaranteed to see the same data, whereas it is in Azure Data Lake. Obviously, having each application deal with this semantic difference would be a pretty big headache. So we abstracted away this difference with an S3 commit service, which basically makes interaction with S3 as strongly consistent as Azure Data Lake, thereby harmonizing the Azure, the data access layer for our data platform factory services. The abstraction layer to handle cloud standards is necessary, but is not sufficient to make our service platform cloud agnostic. In reality, even the so-called common cloud services have quirks that are a pretty big nightmare to deal with if you just try to lift something that's working in one cloud and try to make it work in another. For example, consider virtual machines. With tools like Packer, it's pretty easy to actually create the exact same image in each cloud. So you can actually launch the exact same binary, it's running the exact same code, the exact same operating system, etc. However, when using VMs as elastic compute, the creation time and deletion time of those VMs matters a lot to the user experience. For example, when you're trying to spin up or tear down Spark clusters. And if you're not careful about adapting to cloud limits and APIs, you might end up creating and deleting VMs faster than the cloud can return the quota to you. And you might end up in a deadlock state where you can't actually create more VMs even though you think you have more quota. And this is one of the examples of an experience we ran into that we had basically had to work around in order to make sure that we can create VMs and elastic Spark clusters successfully in both clouds. Similarly, we found that different clouds handle the humble TCP connections very differently. There are a lot of invisible middle boxes that will time out and close your connections without warning. There are small differences in data center network hardware reliability that can cause pretty catastrophic application failures if you're not aware of them. For example, we found that in 2019, there was a major TCP bug in the Linux kernel. And basically what this did is that it caused some TCP connections to hang forever. But we really only experienced this bug in one of our clouds because of very small differences in reliability. Finally, even though you can run things like MySQL and other databases in all clouds, it isn't exactly the same. Things we thought would be trivial, like differences in case sensitivity or insensitivity of the underlying operating system, for example, whether your files can be case sensitively named or not, can reach into the database and bite you if you aren't careful. So to make a truly cloud agnostic platform layer, we are continuously sussing out these quirks and masking them from our everyday developers so they don't have to worry about them. The final lesson I'll talk to you about today is how important it is to use data and AI to accelerate the data platform itself. It actually is really hard to build and operate a data platform without data and AI. You actually need a lot of data and AI to actually build a data platform itself. Thus, Databricks is actually one of its biggest customers, and we use Databricks very heavily. A data platform needs data for many things. It needs data to track usage, maintain security. It needs data to observe users of the data platform and improve it for them. And it needs data to keep itself up and running. And we found that having a simple and powerful data platform like Databricks has been essential to building the data platform itself. Thus, data and AI accelerates the data platform. We use Databricks for many things. And this includes key platform features like usage and billing reports, where we want to deliver actual reports about customers' usage to them, and also our audit logs, where we need to deliver security logs to our customers so they can figure out what their users are doing. We use Databricks for analytics and for feature usage, to look at trends and to model growth, to look at churn and other forecasts. And these are some of the same features that our customers are also using Databricks for. But obviously, we're also a data customer because we use a lot of data to analyze our own product. And finally, a data platform itself is a managed service. And a managed service needs real-time data to operate effectively. And this is for things like mission-critical DevOps and monitoring and observability, so that we can gather and analyze everything from KPIs to APIs and other logs like Spark debug logs, which are necessary both to help our customers debug their workloads and also to debug problems with the platform when there are issues. So to do this all, we've built several globally distributed data pipelines with the Databricks data platform at its foundation. Like our service deployments, we use declarative templates to deploy our data pipelines so that we can rapidly iterate and replicate them. We have a templating tool called the Stack CLI, which you can find in our documentation, that you can use yourself to deploy these data pipelines at Databricks, or in Databricks. Each of our globally distributed Databricks deployment streams basically stream data from ETL data into our data processing engine, which is built on top of Databricks and Delta. But it also tightly integrates with other big data tools like Prometheus, Elasticsearch, and Jaeger for distributed tracing. This allows us to see, analyze, and model the usage and health of the Databricks data platform in real time and historically. Right now, our data pipeline processes hundreds of terabytes of logs per day, and it analyzes millions of time series in real time. This data pipeline has really been essential to the continued evolution of the data platform that is Databricks, that it's actually built on. And thus, Databricks actually accelerates itself. So in summary, the Databricks architecture manages millions of VMs around the world in multiple clouds. We've learned several important things while building this massive data platform. First, the factory that builds and evolves the data platform is more important than the data platform itself. The data platform of the future will not look like the one of today, and the factory is what will build the data platform of the future. Second, a cloud agnostic platform that integrates with each cloud's standards and quirks was the key to building a multi-cloud data platform. And it's harder to do than it first appears because of the performance, scaling, and integration needs of big data. Finally, data in AI can accelerate the data platform features, product analytics, and DevOps. You can't really build a large-scale data platform without actually analyzing a lot of data. And that brings me to the end of my talk. And thank you for listening. Oh, and PS, if you're excited by anything in my talk today, Databricks Engineering is hiring, and I hope some of you out there will come to join us. Thank you.